Okay, so this session we will be talking about the uninformed search strategies, which is also called the blind search strategies. So here we are not using any knowledge about the problem that we are working on basically, but we are just using some systematic search strategies to actually carry out the search. So you don't have any additional information about states beyond that provided in the problem definition. So you need to you need to decide at every point in time which is the node that you are going to choose to expand. Okay, so that is what the order in which the nodes are expanded will change depending on the strategy that you are using. So we have a number of different strategies. Okay, so we'll discuss each of these strategies one by one. So what happens is, if you are using some information about the problem at hand, okay, you come to what is known as the informed search or the heuristic search. So once we talk about the uninformed search strategies, we'll go into the informed search strategies and see how you can use the heuristic information to carry out the search so that you have a higher chance of getting a solution faster. Okay, so that's the reason why you use the heuristic information over there. Okay, so the first strategy we talk about is the breadth first search. So basically this is just a blind search, like we say. So what we are doing is we are taking the root node and expanding it, and once you expand the root node, we get the nodes at the next level. Okay, then all the nodes at this level are first expanded to get the nodes at the next level, and then those nodes are expanded to get the nodes at the next level. Okay, and of course whenever you expand and you get new nodes, you are going to check whether that new node is a goal or not, right? So what happens is that as soon as you find that a node is a goal state, you need to find the path from the start state to that goal state. So we are guaranteed that we are getting the shallowest node, okay, the shallowest path. Okay, so the shallowest unexpanded node is chosen for expansion at every point in time. Okay, so every time you are going to, for example, finish all the nodes in depth 0 before you go to depth 1, and finish expand all the nodes in depth 1 before you go to depth 2. So this shows that as soon as you find a node which is your goal state, okay, the path will be the shallowest path possible. Okay, so if the shallowest path is your optimal solution, then the breadth first search gives you the optimal solution. So what you are doing basically here is that if you consider the frontier, so what did we say is the frontier? It's the set of leaf nodes which are there for expansion. Okay, so what you are doing is that the node which was expanded first, okay, so for example if we take the root node and the root node gives say 3 nodes A, B and C. Okay, if I take A and expand it, I get new nodes which are added on to the frontier, but the oldest node is taken for expansion first. In other words, B is next chosen for expansion, then C is next chosen, and then you go to the next level. So which means that the shallowest node is always chosen for expansion, right? So here if we take the this pseudo code, we can see what is happening here. So you are choosing the node from frontier which you are going to expand. Okay, so the frontier already has the nodes like a queue, right? The oldest node will be first and then the next node will be next, etc. Okay, so you are taking that node, okay, and removing it from the frontier. Okay, and then you are going to add that node to the explode. Okay, then you are finding the actions, right? And you find the child node, okay, depending on all these child node. And if it is not already in the explode or frontier, okay, you check for goal test, okay, and if the goal test is correct, then you return the solution, otherwise you insert it in the frontier. Okay, so this is how the breadth first search actually starts. So what you have here in frontier is a first in first out queue, which means whatever goes into the queue first, that is the one which will be taken out when you pop, right? So this is like a queue. So we have learnt in data structures about queues and stacks, right? So this is like a queue basically. So here if we look at this figure here, okay, so this node is going to expand first and get these two nodes. Then it's taking this node and expanding it to get these two nodes. Then it expands C to get these two nodes, etc. So it will do the nodes at the depth 0, then at depth 1, depth. So it finishes each level of nodes before it goes to the next level of nodes in the breadth first search. Okay, so let us look at the 4 criteria which we said is important for rating the performance. Okay, we can say it is complete, okay, because it will find the shallowest goal node, right? So it is complete, okay, and it will be optimal if the shallowest node is the optimal one, which mostly it is the optimal, okay, unless you have other criteria for optimality, right? So let us look at the time and space complexity, right? The time and space complexity is what is the problem over here, okay? So what happens is that if you start with one node, let us assume that the branching factor is B, okay? So if your branching factor is B, if you take the root node is going to expand to give B nodes, right? And if you take each of these B nodes and you expand those, each of them will give you B nodes, which makes it B squared nodes, okay? And if you take each of those and each of them gives you B nodes, you will get B cubed nodes, right? So what will be the total number of nodes if you are going up to depth D? You are going to get B plus B squared plus B cubed up to B to the D, okay? So you find this is of the order of B to the D, okay? So what you find is that it's exponential in D, right? So as the depth goes on increasing, the number of nodes increases in an exponential manner, right? And if the algorithm applies the goal test to the node when selected for expansion, okay, so when you just put it into frontier, and only when you choose this node for expansion, then only you check whether it is the goal, you will find that you have to go one more level, okay, before you find the solution basically, okay. And what will be the space complexity? Space complexity will be the same as the time complexity. In other words, you need to store all the nodes, okay. So we were talking about the number of nodes here, right? So the number of nodes will be also of the order of B to the D. So the space complexity, time complexity, both are of the order of B to the D, which is really high, okay, because it's exponential. So let us see how this is exponential. So suppose the depth is 2, if we, 4, etc., right? So what you have done is we have taken a branching factor of 10 here, okay. So if we take a branching factor of 10, okay, and we take different D's, okay, so D is your depth, okay. So you find that if your depth is 2, you get so many nodes, if your depth is 4, you get so many nodes, etc., okay. So we can see that the nodes are increasing in an exponential manner, and the time required, okay, so the time required is according to 1 million nodes per second. So it's able to carry out or see to 1 million nodes per second, so expand say. So what happens is that we can see that the 8 nodes takes 2 minutes, 10 nodes takes 3 hours, 12 nodes takes 13 days, 14 nodes takes 3.5 years and 16 nodes takes 350 years, right. So we can see that after some time, because of the exponential nature, you cannot have a very big graph, right. If you have a very big graph, you can't can't wait 350 years, right, to get the solution to what you are looking for, okay. And at the same time, the memory requirement, okay, you need to store all these nodes, right. We can see that with 8 nodes you get 103 gigabytes, okay, and with 12 nodes it's 1 petabyte. You need 1 petabyte to store it, okay, and then it becomes exabytes with when the depth goes to 16, right. So it increases very fast, the amount of space that you require, amount of time that you require, right. So this is not really practical for very big problems, okay, maybe okay for small problems. So suppose you just put your computer on and you ask it to find the solution and it goes on for 350 years because you have not calculated how long it's going to take, then it's something which is totally impractical, right. So that's the problem with the breadth first search, okay. So first, the memory requirements are a bigger problem for BFS than its execution time, right. We have seen, right. So we can see in general, so this is the conclusion, exponential complexity search problems cannot be solved by uninformed methods for any but the smallest instances, right. So BFS is not practical for larger type of problems. Okay, so if we look at BFS, is it complete? Yes. Time complexity, order of B to the D. Space complexity, order of B to the D. Optimality, yes, it gives you the optimal solution. So next, we are going to talk about the uniform cost search. So what we are doing here is that in BFS, what we did is in breadth first search, we chose the shallowest node or the node which was expanded first, and we expanded those nodes, okay. But here what we are doing is in the uniform cost strategy, we are finding the one with the lowest path cost, okay. So the lowest path cost is the cost from the source node to this particular node that we have, okay. So what you do is that um, in the frontier, what you are going to do is you use a priority queue, right, and put the nodes according to the path cost, okay. So the one with the minimum path cost is put one first, okay, then you find the one with the next path cost, etc. So you are using a priority queue there and you are drawing out the node with the minimum path cost at every point in time, okay. So let us look at this algorithm. Yeah, so this is the algorithm for the uniform cost strategy. So you have a priority queue over here, right, to draw out the node, and when you expand the node, okay, you need to calculate the path cost, okay, and according to the path cost you have to add it into the priority queue, and when you expand the one with the lowest path cost at every point in time, okay. So this would be something like saying that if we have say one node here, okay, and we expand, okay. So the path cost could be in the case of this problem here, it could be the time or the distance between, for example, from CBE we can say it's distance between this node and this node, okay. and the distance between this and this. So these are the two nodes, and you see that this distance is larger than this distance, right? So the path cost of this will be smaller than the path cost of that. So suppose I have a path cost of 10 on this and 5 on this and 4 on this, right? So it will take the one with the lowest path cost, okay, maybe this one, okay, and it will expand this, right? Then what you have is you have this node, these three nodes in the frontier, right? And each of them will have a path cost. So when I get these nodes, I'm going to get the path cost of this as the path cost of this plus the cost of going from here to here. Okay. So you have each of these nodes will have a path cost. So you check all these path costs and choose the one which has the minimum path cost and expand that at every point in time. Okay. So that is the way this uniform cost strategy actually works. Okay. Yeah, so what happens here is that the goal test is applied to a node when it is selected for expansion, right? Rather than when it is first generated. Okay. The reason could be that you could find another node which has a lower path cost, okay, than what you are working on. So that is the reason why this is done. Okay. So you have the example shown in this place over here, right? So what you are going to do is because you are expanding this to get these two nodes, and because this has a smaller value than this, right? So you are going to choose this one for expansion, right? And you are going to get this node, okay? So this will be 97 plus 80, okay? But once you do this, you are going to see that 99 is smaller than 80 plus 97. So you are going to expand this one. And since you are going from Sibiu to Bucharest, this will be your goal state, right? But you are not going to stop there because it's only when you choose it for expansion that you will be able to say that it is the goal state. So then again you see that you need to expand this one. So when you expand this and you again come to Bucharest, you find this has a smaller value than that, right? So then you are going to choose this path instead of that path, even though that path was got before this path. Okay, so that's the reason why you're checking the path cost. You're checking whether it's a goal state when you choose it for expansion, basically. Okay, then we come to the depth first search. So in the depth first search, you do what is called the last in first out. Okay, so in other words, you are going to choose one node and you are going to go to the deepest level with that, right? And once you find the deepest level, then if you still don't find a solution, then you backtrack and then search another node, etc. Okay, so that is how the depth first search will work. So if you say take node A, it's going to expand node A to get B and C, then you take node B and expand it to get D and D, then you take D and expand it to get H and I. But if H and I don't have any leaf nodes or any nodes, okay, it cannot be expanded any further, you are going to backtrack, right? So when you backtrack, you come here and you are going to expand this. Then you go back like this and you come here and then you are going to expand this, etc. Okay. So that's how the depth first search actually works. Okay. So if your goal is say M here, okay, you have to then go through all these things till you come to M. But at the same time, if your goal state had been somewhere here, then it would have found the goal state fast. Okay. Okay. So what happens is that many times you cannot check the depth first search to go to some level D, right? Suppose you say that you are going to go to a level D till there are no more nodes to be expanded, right? You may find that infinitely you keep on going down. So generally what happens is you choose one depth M and you say that M is the maximum depth up to which you are going to go. But what happens when you do that is that if there is a goal state which goes, at a greater depth than M, then you find that you are not able to get that the solution at all. Okay. And when you come to the storage, okay, the storage here is order of BM. So you find that storage is much lower than in the case of the breadth first search. Okay. So it's something like this. Suppose I go along these nodes, okay, and I finish searching here. So when I come to search E, then I don't need this information anymore. So it can be removed from your memory. And when I finish here and I come here, I can remove this whole thing from the memory. So I need only this part, okay. And once I have done with this and I come this side, I can remove this part from the memory, okay. So because of that, you find that the memory that you require for depth first search is much less than what you require for the breadth first search basically. Okay, so what is the problem with the breadth first search? With the depth first search is that how do you choose the value of M or the maximum depth up to which you are going to go, right? So you may not know up to which depth you have to go to find a solution, okay. So what happens is that if your M is too small, then you find that you may not even be able to get a solution. But if your M is too large, okay, then you find that you need a lot of extra time to find a solution, extra space to store the information. So unless you have some information on what your M is, okay, you find that using this depth first search becomes very difficult. So what happens, what is the overall thing? Completeness, yes, okay, assuming the state space is finite. If we don't have that M, right, and you are going to go down till say D, right, the maximum depth, and then come back, the state space should be finite, only then it will be complete, only then it will be able to get a solution. Time complexity can do well if there are lots of goals, right? Otherwise you may have, it will be just like the breadth first search, the time complexity. Space complexity is order of n deepest point of search, where n is the deepest point of search. So space complexity is good. Optimality, no, you are not sure that you are going to get a solution at the deepest level. So when you say depth limited search, again you are choosing L, okay, a predetermined level L, okay. So again it's just like choosing M. So if you take L equal to infinity, it can be viewed as just the depth first search. Okay, if you take L to be something less than infinity, then you get the depth limited search basically. So in some cases you can actually estimate what would be your L. So if you are able to estimate that L, then using depth first search could basically help you. Okay. So this is the depth limited search over here. Okay, where recursive depth limited search is used. Okay, so you carry out the recursive DLS on the child. Okay, so it's a recursive procedure that is being used, and you are using a cutoff here. So you're seeing that that's a depth limited search part. Okay, if it goes beyond the cutoff, then you stop basically. Okay, so depth limited search. Uh, is it complete? No, if L is less than equal to D. Okay, you may not be able to get the solution. This is the time complexity, space complexity, depending on L, and you are not sure whether it is optimal or not, basically. Okay. So, we'll stop this session here, and we'll do this iterative deepening method and some other methods which come under uninformed search in the next session. So, we'll stop this session here.